In that case, we'll take a look at the review document. Version 2 is the one I handed out, I think. I've got some highlighted. Hopefully we can get through these before I run out of time. Let's see. Yeah, there we go. Okay. Number 1. If the reaction is first order based on this reaction, and iodine, ion. Should have known better. And this is I3 plus 2H2. Okay. We're told that this is first order in hydrogen peroxide. Second order in iodide, and zero order in H+. Which of the following rate laws best is preferred format? So we know how to write the rate law. We just say rate is, and we're working from, based on the information they give us, we're working on the disappearance of reactants rather than the appearance of products. I don't know of anybody that does appearance of products expressed in maybe in special cases. It's usually disappearance of the reactants. Okay, and then iodide, and then hydrogen. And we're told that this is first order, right? This is second order, and this is zero order. So what's the preferred format? That's not it. Nope. If that's zero order, it's 1. So that one's out of there. Okay. That's the, well, we got my constant. That's the preferred format. Now, if you're given this general rate law for that equation, you know that all 3 terms have been identified. But if it's not in the rate law, that means this is zero order automatically. All right. Number 2. It's going to be difficult. All right. Bring up the goods. I'll fix that when I sprayed the board. I'll do it. Okay, number 2. A reaction has the rate law, rate equals K times A squared, B to the first power, and C squared. What's the overall order of the reaction? This is just definition. Right? The overall order is just the sum of the individual orders. Right? So it should be 5, correct? 2 plus 1 is, and 2 is 5 is the overall rate. All right. I'm going to skip this one because this one is very involved. I've got another one that's a little more time sensitive. Let's go with 4. If the reaction 2HI equals H2 plus I2, okay, is second order. Since we only have 1 reactant, we assume that's second order. So we would write it rate equals A times HI to the second power. Which of the following would yield a linear plot? All right. Remember the method I gave you for determining what order? If you take the raw data and versus time, and you just say the concentration of A you'll get a straight line. If it's zero order, if you plot natural log of A against time and it's first order, then you get a straight line. If you take the inverse of A against time and it's second order, then you get a straight line with a positive slope. So the one that works is the inverse of HI versus time, right? B. Yeah, it's working better. Conquer the world with WD-40 and duct tape. Number 5, let's see. Which of the following statements about enzymes is incorrect? All right, what's an enzyme? It's a biochemical catalyst is what it is. Only it has unique characteristics as compared to inorganic catalysts. Inorganic catalysts tend to accelerate the reaction in both directions. Enzymes tend to accelerate the reaction in only one direction, with a few exceptions. So, which is incorrect about a catalyst? They're usually proteins that catalyze specific biological reactions. Yep. There are a small number of them that are based on RNA. Most of them are proteins. B, they are equal to inorganic catalysts in efficiency. That's false. They are far, far superior to inorganic catalysts in efficiency. It's just, there's no comparison. Several thousand are now known. Yeah, it might even be tens of thousands by now. The molecules they react with are called substrates. We didn't cover that in class, but that's true. Enzymes react with substrates. So B is the false one, the efficiency question. About 8. A free radical is a chemical species that possesses what? An unpaired electron. So D is your correct answer. About 9. The rate expression for a particular reaction is rate equals Ka B squared. A first power and B the second power. Right. Now what's the question? If the initial concentration of B is increased from 0.1 to 0.4, so we go from 0.1 for one experiment and we increase that to 0.4 molar, the initial rate will increase by which of the following factors? Well, what's the ratio? It increased by 4 times, didn't it? Okay, so 4 squared is 16. We would increase the rate by 16 times if we did that. Yeah. If we did it to this one, it would only increase by 4 times. The initial rate, that is, initial rate. All right, number 10. For which order reaction is the half-life of the reaction proportional to 1 over K? So let's look at 0, first, and second order reactions with respect to half-life. This is the one I can remember. This one, 693. Okay. How about this one? You can look it up if you want. I know I'm gonna have to. Because I don't use it every day. If I did, it would be right at the tip of my tongue. Okay, this is A over 2K. Okay. And the last one, probably A on the bottom. Yeah, 1 over K to A. 1 A times A 0. I think I covered this in class. They're all proportional to 1 over K. Half-lives are all proportional to 1 over K. All right. 13. Of the following choices, which type of collision is most likely to be the rate determining step in a proposed mechanism? Well, if you have these choices, you want to find the one that's the least likely. It's going to be the slowest. And the least likely out of all of these is termolecular, where you have 3 species, 3 molecules that have to come together with just the right energy and just the right orientation for the reaction to proceed. And termolecular is the probability of a termolecular step, elementary step in a mechanism, is almost nothing. Non-molecular, I just made that up to fill in the space. So that's our answer for that. 14. Let's see. We're going to decompose some hydrogen peroxide. There we go. Yields. How many? Wait a minute. Oh, this is the overall reaction. Okay, I got you now. Plus O2. And we're saying that it has this following mechanism. So the first step, right, step 1, is one of those hydrogen peroxides reacts with, and we should have put this right up here, iodide ion. Okay, and this gives us water and that intermediate. Then we take the next one, X2O2, and it reacts with that species and makes another water plus an oxygen plus iodide. Okay, this is step 2. Now what's the question? The catalyst in this reaction. Well, I told you what the intermediate was, right? Intermediate is something that's produced in one step and consumed in another. All right, so this would be an intermediate here. A catalyst is something that goes in the front and comes out the end, apparently unchanged. But it is integral to the mechanisms, the reactions. It's intimately involved in those reactions. It has to be in order to do what it does, to reduce the activation energy for the overall reaction. So the catalyst in this one is iodide. Now, what type of catalyst is it? Homogeneous or heterogeneous? This all happens in solution. This is a homogeneous catalyst. It's usually introduced as potassium iodide. It doesn't have to be, right? Any iodide will do. But that's probably the cheapest and guaranteed to be soluble. Right? All potassium salts are soluble. Right? If we picked a different one like calcium iodide, it's probably insoluble. Let's see. We're gonna skip that one. Let's see. Okay. All right, here we got one where we're going to answer a question, the order of the rate law for MnO4 minus. We're going to use these series of initial rate experiments to answer the question. So let's make a lot of room, 17. And if the overall reaction is 2MnO4, let's see, let me put it over here, 2MnO4 minus plus 5 H2 C2O4. It's probably oxalic acid. And 6. Some extra acid yields. And this part of the equation is essentially irrelevant once the equation has been balanced. Of course, you need it to balance the equation, but when we get to the rate law part, we don't need that. We only need this. And I write it that way so that I can put the information underneath it. They've got the rate on the right-hand side. I like it on the left-hand side. So we've got 2 times 10 to the minus 4. 2 times 10 to the minus 4 molarity per second, right? And then 8 10 to the minus 4, and then 1.6 10 to the minus 3. Okay, so what are the concentrations? Well, if we do like this, that's all right. Then we can put the values in here, save ourselves a lot of extra writing. See, this one's 1 times 10 to the minus 3, and the rest are 2s. Okay. First of these is 1s, then 2s. And then hydrogen ions are 1, 1, 1, and then 2. Okay. All right. So if the question is pertaining to MnO4 minus, the manganate ion, we want to know the order for that one. We need a rate law. And the rate law for this one is going to be, let's see, let's write it like this, equals the rate constant, and then MnO4 minus to the, let's see, that I did N first, didn't I? Got to be consistent. Then oxalic acid, M, and then H plus P. Okay. So next step is ratio. Right? We need a ratio of 2 of these that allows this one to move, this one to change, and keeps these 2 constant. And it looks like the first 2 worked best. Right? This one changes, those 2 don't. Now, depending on whether I prefer to put the bigger one on the top, it really doesn't matter. But I think it's easier to proceed with fewer steps. If you put the bigger one on top, that gives you a whole number or a positive number rather than a fraction. So if we write the rate here times 10 to the minus 4 over 2 times 10 to the minus 4, that's equal to, and then we have K on top, K on the bottom, and then we have these guys right here. Well, these are going to be equal on top and bottom, so they go out. Right? They cancel out. Well, what we have here is this one on top, 2 times 10 to the minus 3 to the n, and this one is 1 times 10 to the minus 3 to the n. Okay, A's go out also. And one of the rules of math is if we have the numerator to the n power and the denominator to the same power, it's the same thing as dividing these two together and then raising them to the n power. So this would be equal to, that's what, 4? That's 4. And this is 2 to the n power. So n would have to be 2. This would be second order in manganate. We could do the same thing for each of the others. Which ones will we pick if we were trying to figure out this one? Well, let's see. We got to keep these together. They have to stay the same. So it's either one of these three. And we have to let this one vary and this one stay the same. So we'd use this one on top and this one on the bottom. And then it would be 2 divided by 1 would be 2. 2 to the m power. But this ratio would be different. Okay? This would be 8 on the bottom. And if we change this one to minus 4, right, it would be 16 times 10 to the minus 4. Correct? So then I would put 16 over 8 would be 2. Right? That would be 2 equals 2 to the m power. M would be 1. Right? I didn't have to write that up there. See where I'm going? Okay. And then might as well do hydrogen as well. So let's see. Hydrogen, we want this one to be variable. So we put this one on top and this one on the bottom. Right? 1 point. Well, we've already got minus 4, so 16. 16 and 16, so that's 1. And this ratio is 2 divided by 1, which is 2 to the p power. How do you get 1 out of a number to a power? The power is 0. Right? So this would be 0 order. Okay. I figure while we're at it, might as well do them all. All right. Let's see. No, 18 doesn't have anything to do with that diagram. 18 is independent. So let's do 18. If you haven't worked at least a few of these already, what I'm saying up here is just going to sound like Sanskrit. The rate law for this reaction is, okay, NO squared O2. Rate equal K NO O2. Yeah, O2. Okay. We have 2 reactants. We have 2 terms in our rate law. Okay, that's good. What happens to the rate when the concentration of O2 is tripled? We did one like this already. If we triple that concentration and it's to the first power, then we triple this one. It's that simple. What if we triple this one and then we triple this one also? Well, this would be 3 times, but this would be 9 times, which would be 27 times the rate increase, wouldn't it? Okay. All right. Let's see. I think I've got another one down here with that type of diagram, so that's why I skipped that one. So we move on down here to 24. We'll get back to that energy diagram in a minute. What fraction of a reactant remains after 5 half-lives of a first order reaction? Well, actually, remember what word problems, their primary purpose? To confuse, right? They put information in here you don't need. When we say what fraction of a reactant remains after 5 half-lives, that's all you need. It doesn't matter if it's first order, second order, or infinite order. 5 half-lives means that after one half-life, right, we start with some reactant. And after one half-life, we got a half of it left. Right? So this is the first half-life. Second half-life, this becomes a new A0. This one is half of that one. Right? Third one, fourth one, fifth one. So we keep taking half of each one. And then we get to the fifth one, A0, and we take a half of that one. So what's a half of a half? A fourth, right? A half of a half is a fourth. And a half of a fourth is an eighth. And a half of an eighth is a 16th. And a half of a 16th is a 32nd. So we actually only have, yeah. If this is that one, then after 5 half-lives, we only have a 32nd of it left over. The other way to do it is like this. 1/2 to the n. 2 to the 5th power in the denominator is 32. But I figured this makes more sense for most people. If you're a math major, then I'd go straight to this. Okay, who's next? Let's see. 25 is based upon two A sub 2, B sub 2, 2 A sub 2 plus B sub 2 yields 2C. The first step in our mechanism, step number 1, is one of these combines with that one and yields this intermediate plus one of those. And then step 2, and this is the fast, right? But this is very slow. The second one is we take another one of these and we combine it with that intermediate, and that yields, or rather C. So which step is rate determining? This one, the very slow one. Okay. Now, if we were to try to write a rate law for this one based upon the mechanism, right? First of all, does it meet the first condition? We add these together, we got 2 of those, got 1 of these two cancel, we got 2 of those. Yeah. So the rate law, the mechanism is consistent with the overall reaction. If we were to start writing a rate law for this one, we would say rate equals some K value times that one to the first power, and that one to the first power. But we couldn't stop there because this isn't present in that one. So we'd have to, this fast reaction is probably both directions. It doesn't say, but that's, and then we would go from there. But that wasn't the question. I'm just speculating. How about 26? For this reaction, A yields products. Let's see, A0 is 6.4 molar. So let's see, let me read the rest of it. The first two half-lives are 60 and 30 minutes respectively. If this reaction is known to be zero order, calculate K. Okay. So we've got a table over here where the concentration of A is here. And we're starting out, the first concentration is 6.4 molar. And there's your time, 0. So after the first half-life, which takes 60 minutes, this concentration should be half. Okay. The second half-life is only 30 minutes, which would be half again, would be 1.6, right? Okay. That's given information. If this reaction is known to be zero order, if it's zero order, goes K and 0, which is equal to K. What's the half-life? How do we write the half-life of that? T1/2 equals what? Well, we know K is in the denominator. Where's A? Actually, it's 2 times A, isn't it?
I think it's 2K.
Oh, 2K on the bottom. Sorry. I put 2 in the wrong place. There we go. A0. Okay. Well, if we're told it's zero order, then we can pick either one of those. Right? If we say A0 is 6.4 and then 2 over K, then the half-life would have to be 60 minutes, right? And we could solve for K. Right? 2K comes over here, and 6.4 divided by 60 goes over there. So I put that one over here, this one over there. And then K then equals 6.4 over 120, 60 times 2. All right, the answer is there. 10 to the minus 2. Now, if you weren't told it was zero order, we would have to go through and run each one. Except we wouldn't have to run first order because first order is not dependent upon concentration. Right? It's just 0.693 over K. Right? So we would do first order, we'd do zero order and second order using that data and see which one gives us a true constant K. Right? I think I did one of those in class. And that would confirm, in this case, it would confirm that we have zero order. All right, let's see. Okay. Following question refers to 2a squared or b squared equals 2c. Wait a minute. No, it doesn't. That one's out of place. That one belongs up here, doesn't it? That preceding information there has nothing to do with 27. It got messed up. 27 stands alone. According to the collision theory, the activated complex oh, yeah, it is. Yeah, it is. Okay, I'm sorry. The activated complex that forms in step 1 could have which of the following structures? Dotted line represents partial bonds. Remember, in the activated complex, or that's good enough a name. Bonds are breaking and forming at the same time. They're not complete yet. We've reached the hump. So if we have in the first step, which is the very slow step, a squared and b squared. So we would have a with some kind of bonding and then b with some kind of bonding. But the first step doesn't have, it does have b in it. Okay, so when these two come together, what we end up with is bonds breaking here and bonds forming there. Yeah. You're not going to have, and this is an artifact of the way Word does things. A is this group up here, and B is this group. It's almost as if you think A is between C's and A's, but it's not. So, let's see. So the second one would be like this. That's the activated complex. Right? We don't have R yet. We don't have C yet. We only have these two coming together, and that's at the hump. Okay. All right, there was another one. How about this one? 31. Oh, 1025. That panic. The rate constant for a reaction at two different temperatures is given below. What's the activation energy for this reaction? Since we have two temperatures and two constants determined at those temperatures, we can use, let's see. Let's look at your copy. My copy has correction in it, and I think I made the correction. Yeah. Yeah, that's right. Yeah. So we would use this modification of the Arrhenius equation, which incorporates two temperatures and two K values. So we would have natural log of, see, I think I used parentheses, K2 over K1 equals E sub A over R. And then we have, which one comes first? I don't think it matters, eh? Oh, it's minus. So 1 minus 2. T1 and T2. Is that correct for yours? I don't trust mine. This is an old copy and
Yeah, that's
it's
right.
one minus two. Okay. All right. So we just have to keep our ones and twos associated with each other. The temperature here, the first one is going to be 30 plus 273. Right? It has to be Kelvin. This one's going to be 49 plus 273. R is 8.3145, is it? Yeah, 3145. And E sub A is our unknown. And this second K is at the higher temperature. So it's 1.21 times 10 to the minus 3. 1.21 times 10 to the minus 3. And the lower temperature is 1.38. 1.38 times 10 to the minus 4. So I'm going to resolve these two first. I'm going to ratio these two values, 1.21 to the minus 3, and then 1.38 to the minus 4. Divide those. This will be the natural log of 8.7681 equals. And this is going to be, let's see, I'll just keep this as it is for now. 8.3145. And figure out what this is. All right, that's going to be 303, isn't it? So this is 1 over 303 plus 1 over 322. I think. Yeah.
Mm.
One little mistake. Send your space probe off course and it smashes into Mars. Okay, let's try that again. 303 inverse and 322 inverse subtract. Now we got 1.947 times 10 to the minus 4 divided by 8.3145. And that gives us E sub A times 2.342 times 10 to the minus 5. There we go. So now we divide this one by that one. 2.1711. Flip that one. Divide. This gives us E sub A equals 9.2696 times 10 to the minus 10 to the fourth joules. Okay. If we remove 10 to the third of those and make a kilo out of it, that leaves us with 10 to the first power times this, or kilojoules would be 92.7 kilojoules. You guys got to stay on your toes.
I try and then I get confused myself.
All right. 32. Consider the following balanced reaction and experimental results that follow. Okay, so we've got 3 experiments. We've got, this is initial rates experiments. We've got 2 reactants. That means we need 3 experiments in order to give us all possible combinations. So what's the rate law orders for NO and H2? All right, I'm going to do it this way. The rate equals K times NO to the N and H2 to the M. So I'm going to draw from that table. We want the first one to give us K over K, and then whatever, we're going to do NO first. So NO can change, but H2 cannot. H2 doesn't change between the first and the third, but NO does. So NO, if we put the third and the first one for NO, that's 0.03, 0.015. K's are the same, so they cancel. And then the NO concentrations would be, oops, I used the wrong values. This is 0.030. This is 0.015. And then the rates, I forget, they put the rates on the right-hand side. The rates then would be 2.4 and 0.6. 0.60. And this one is the same for both, right? So it cancels. And this is N and N. That cancels. So we're left with 0.6 into 2.4 is what? 4. And this is 2 to the N, right? So N is equal to 2. All right, for H2, we just change these values. Now this one's going to go out. And we're going to use the first and the second one, because the first and the second one gives us NO the same. And 0.04 over 0.02, 0.04, 0.02 to the M. And the rate the rate is 1.2 and 0.6. So that's 2, and that's 2. So M has to be 1. Okay. So if it's asked us for NO and H2, so it would be 2 and 1. 2 and 1 answer. Now, what if we want to find out what K is? Now that we know what the orders are, we just take the rate law, pick any one of those experiments, just pick the first one, 0.6. 0.6 equals K is now our unknown. NO for 0.6 is 0.15 squared, and H2 is 0.02 to the first power. So then we can square 0.15 is 2.25 times 10 to the minus 2. And then multiply that times 0.02. That's 4.50 times 10 to the minus 4. And then that's in the numerator, so we divide that into 0.60. And that's equal to K. 1.33 times 10 to the third equals K. That wasn't part of the question, but if you ever are asked to do that, that's how you do it. Once you've got the orders from here and here, you take any one of these experiments and plug in the values and solve for K. All right. Let's see, 33. First order decomposition of H2O2 at minus 28 C occurs with a half-life of 50 seconds, starting with a concentration of 25.2 molar. What will be the residual concentration of H2O2 after 5 minutes? Okay. Let's put what we've got up here. First order in H2O2. The decomposition of H2O2. Right? They're just saying it makes products. And we know it's going to be O2 and water. O2 and water. So that means we need 2 here and 2 here. But if it's first order decomposition, that means the rate is equal to some K value times H2O2 first order. And this is at minus 58, was it? No, minus 28. 28 degrees C. Okay. And we're also told that the this half-life of 50 seconds. E1 half equals 50 seconds. Okay. We're told it's first order, so we know what the relationship is here. This 50, is it 50.0? Yeah, 50. This half-life here is first order, so we know that it's 0.693 divided by K. Right? Okay, so we can tell what K is. Okay. K is equal to 0.693 divided by 50. And that's 1.39 times 10 to the minus 2. So, starting with a concentration of 25.2, what will be the residual concentration after 5 minutes? Okay, we can't use the half-life beyond this point because the time is not half-life increment, right? So what we have to do is use the integrated rate law for first order, which would be natural log, wouldn't it? Minus KT. Log of, oops, be a log of this equals minus K, 1.39 times 10 to the minus 2 times the time. And this is in seconds. And our new time is in minutes. So how many seconds is that? 300 seconds, right? I'll plug that in just a minute. And then the natural log of the starting concentration, which was what?
25.2.
Yeah, 25.2. There we go. So now we have an equation in one unknown. Natural log of 25.2 is 3.2268. And then, oh, time. 300 seconds, right? So 300, 1.39 exponent minus, and this is minus 4.17 plus 3.2268, right? That's what this term is right here. Which would be, let's see, I've got them both in my calculator and just say plus. So this is minus 0.9432. That's equal to the natural log of the concentration which we want. So how do we get from here? From here, we take the anti-log of this value, the anti-log of that value, which is e to the x. So if this is our x value, we just find our e to the x key. And, well, if I'd have done it right, it would have worked. There we go. And H2O2 concentration after 5 minutes is 0.389 molar. Nah, close enough. 394. I don't know what I did wrong. Maybe I didn't do anything wrong. Looks kosher. Up to that point, 0.432, change the sign. Take this one. Yeah. How does it look in work problems? Did I end up with that answer up there? 0.394?
Yeah, I don't understand. Per second, we have
5 times 60 is.
is that what that is? I thought it was 5.
No, 5 times 60 is 300.
I don't know how.
Let's see. Where did this one come from? This was here. So did I put the right value in there? 693. 0.693 divided by K?
Yes.
Okay. 0.693. And swap places. Is that right? 50 seconds.
I think you just rounded more because here you have 1.386
Uh-huh.
and up there
That's
you
it.
put 1.39.
If I use 86 here and use 86 here, 300 times, and then 3.2268. This would be 9312.
Yeah, that's what you got right here.
Okay, then we would end up with 394. Okay, so pick the best answer. Get this out of the way. Number 34. Yeah, when you got when you introduce a rounding error into logarithms, the absolute difference can be way, way off. Probably be worse if we were using common logs because they're base 10. Base E is like 2.313 something. So it's a little more forgiving. Okay, let's see. For the second order reaction, NO plus O3, ozone yields NO2 plus O2. The rate constant has been measured at 298. The activation energy has been measured over this temperature range. What's the rate constant at 233? Okay, so for this one, we're going to use that Arrhenius equation. Right, the log K2 over K1. K1 equals E sub A over R. And then 1 over T1 minus 1 over T2, correct?
Yeah.
Okay. We just have to decide which value goes where. So the question is, what's the rate constant at 233? If we know 298, 298 is higher than 233. So I would put K2 at T2 equals 298K. And K1 is T1 at 233K. Yeah. And then E sub A is 11.4 kilojoules. But the R is in terms of joules, not kilojoules. So you have to convert E sub A from where was it? 11.4. 11.4 kilojoules is equal to 11.4 times 10 to the third joules, or 1.14 times 10 to the third joules. Okay, so there's our E sub A. There are temperatures. R is constant, and we know what 1.08, this K value for the higher temperature at 298, 1.08 times 10 to the 7th. There. Now everything's assigned to its variable. Now we can plug them in the equation. So we got log of K2, which is 1.08 times 10 to the 7th, and then K1 down here. And then E sub A is 1.14 times 10 to the 4th joules over R, which is 8.3145. Which is joules per mole K. And then we have 1 over T1, which is 233, minus 1 over 298. There we go. Now our equation's set up. All right, we can resolve this side into a single value. So let's say 233 and take the inverse of that, and then 298, take the inverse of that and subtract. And then I got 9.36 times 10 to the minus 4 for this one. Then times 1.14 exponent 4 and divide by 8.3145. So this, if I did it right, is 1.2835. Okay, that's equal to this term. All right, how are we going to get at that? Well, here's the way you do it. You use an identity of logarithms, right? The logarithm of A over B is the same as the logarithm of A minus the logarithm of B. So we'll take the logarithm of 1.08 times 10 to the 7th minus the logarithm of K1. Okay? So what's the logarithm of 1.08 10 to the 7th? Natural log of that is 16.195. 16.195 is this one. So I'm going to move this one over here to make it positive. And then this one brings that one over here, makes it negative. 1.2835. Okay. So that's where we're at now. Let's see. I'm gonna flip those so I can subtract. There we go. And this is 14.91 equals log of K1. And now we just take the anti-log of 14.91. And I get 2.99 times 10 to the sixth. Is that close? Yeah, rounding error. 2.96 is the answer given. Everybody follow me on that one? Let's see. Who's next? Oh, we skipped. There's a lot of repetition in here. Okay. So now we're going to come down to our energy diagram. And this, what we're trying to do here is determine if you can read this diagram correctly, extract information from it, interpret what it's trying to say to you. So we're going to use that diagram for 39, 40, and 41. 39, 40, and 41. Okay. 39 says, which letter shows the activation energy without a catalyst? So if you know that activation energy is, without a catalyst is shown in the red trace, then the high point there, that big hump, would be the activation energy. But it's activation energy from what point to what point? It's from where the reactants used to be to where they are at the top of that hump, which is E. Right? That's the uncatalyzed activation energy. Which letter shows the using a catalyst? Okay, so the blue trace gives us the catalyst. And we're starting from the same point, wherever the reactants are, to the top of that blue is A. And the last one is, which one shows the activation energy for the reverse reaction without the catalyst? So we're back on the red trace, and we're going from products to the top of that hump, which would be C. All right. Yep, C. Let's see, is there anything we missed in here? How about the enthalpy of the reaction? Energy change from reactants to products.
Yeah.
Yep. Going from reactants to products. And since product, if it's final minus initial, the final is a lower value than the initial. So the final minus the initial is a negative number. That means it's exothermic. Yep. And it would be endothermic going back the other direction. It would just be change the sign. Now, it'd be more difficult to go backwards because you need more energy. All right, let's see, who's next? Oh, got this one. Let's see. I think, yeah, 42 and 43 are based upon that that diagram. Okay. 42 and 43. What are we looking at here? Natural log of SO2 Cl2 over time. And it looks like with a negative slope, it's disappearing over time, right? It's a natural log expression over time, which is the integrated version. And natural log trace would be first order, wouldn't it? Right? So the first order is going to be, let's see, let me go out here. The first order is going to be natural log of this species at any given time is minus K T plus the natural log of the starting SO2 CL2. There. Okay. So this is a straight line version with a negative slope, which corresponds with that. And if we look at the expression there, y equals, so this is our y, and then we have negative 2.20 times 10 to the minus 5 x plus, well, actually it turns out to be a minus 8.87 times 10 to the minus 5. Okay. So when I lay it out like that, it should be obvious that at any one point in that curve, we can find this value as long as we know the slope, we know the amount of time that's elapsed, or read the time off of the chart, and this is the y-intercept. Okay, so what's the question? What order is the reaction with respect to? Well, we already determined that, but first order. Because we're plotting natural log against time, and we're getting a straight line. Right? How about the value of the rate constant? Well, the rate constant, well, I'll put the values up here already. The rate constant is going to be, it's a negative rate constant times time. So this is the rate constant right here. Right? That's K without the negative. So it's 2.20 times 10 to the minus 5, which is B. Okay? That's how you read that graph. That's it, isn't it? Okay. Are there any other questions? I know we skipped a bunch of them, but I wanted to be sure we got finished before we ran out of time.